So hopefully you guys have, I know you guys, because I heard about it. I don't usually do the active examples as much as I did this last time, but I feel like they're really good because it gets you to start thinking about forces. So let's start thinking about forces. So a force, if you get Newtonian physics for babies, a force is going to look like, and we'll call this a contact force. And that would be a push or a pull. And we're familiar with those, okay? We're familiar, if I have a push and a pull, we're very familiar with those. Now, there's a couple of other things that we deal with, and we're going, well, wait a second, you talked about Kepler's laws, and you talked about Cavendish, and you talked about these other folks, and Newton was really trying to solve a problem. And the problem Newton was trying to solve is here's the Earth, and then we got our moon over here. So why is the moon and the Earth sitting there as a separate system? Well, that's a different kind of force that we have. It's still a force, and actually Newton's universal law of gravitation is just a special condition of our forces, but this we can also refer to as a field force. And we can represent our field force by using some arrows. And it's a little weird when we start talking about a field force in terms of our mechanics systems, because we're not as comfortable with this. Our world lives on, we put our feet on the ground and we're sticking there on Earth, and we don't normally tell that there's any change in our field force. But if I have two magnets, right? If I have a magnet and I have a North Pole and a South Pole, we know exactly what's going to happen. These two things are going to attract, and we can actually feel this field force in terms of our magnets. So when we're talking about this gravitational force here, our gravitational force is going to be a field force. So we have contact forces and field forces, but we're going to start out with our contact forces, and then we'll come back to our field forces. So we're going to start out with pushes and pulls. So let's think about this for a second. The lab that you're doing right now, the one that's due this week, is related to something like this. I have my IO lab, and I'm going to pick it up by this little piece, and I'm going to raise it up. So what I'm doing is I'm overcoming the force due to gravity to lift it up. And so we're actually going to get something that we're very familiar with the idea of weight. And weight is our force due to gravity acting on my object. Okay, so we know that if I have a small item, it's going to take less force to move it up than if I have a bigger item. And one of the things that we know, and this is one of those things that we know, is if I have an object here and I'm going to apply a push to this, in order to get this to move, this object has mass. And the more mass this has, the more of a push I have to apply in order to get this thing to move. And this gives us this idea of inertia. And so good old Newton talks about this idea of inertia. And inertia is related to mass. And the more stuff or the more mass I have, the bigger the push that I have to do in order to get it moving. That's the thing that I've got to deal with in order to get that thing to move. So he's actually saying that force is proportional to mass. And if I look at it and I do with my wheels down, if I'm doing my experiment where I have my little cart and I've got my wheels here, and I pull this and I'm going to apply a force, and we're actually going to be able to measure that force. And we're going to get if I look at that and I'm measuring this and I do a force versus acceleration plot, we're going to get data that kind of looks like this. And the slope of this is our proportionality constant, which is going to equal the mass. Now I can do that again, okay? And this time I put, let me say I put a soda can on top of my little car. So we have a bigger mass. Well, guess what happens? If I have a bigger mass, my force is going to I'm going to change the slope of this because it's proportional to mass. So this idea, this is what we're exploring when we talk about Newton's second law. And what we're saying there is that the sum of my forces, and we talked about this a little bit last week, the sum of my forces is going to equal mass times acceleration. And force and acceleration are vector quantities. Because mass is just a scalar. It's just the amount of stuff that I have. That's all I got. It's just the amount of stuff that I have. Now, that's not what Newton said. Okay, so Newton, this is a special form. That's a special form of Newton's second law. And I'm going to show you that in here in just a second. So let's look at this, and let's look at this for a couple of different ways. So just like Skylar had asked, what we're going to do is we're going to take and we're going to apply a force, and we're going to actually measure the force applied. So let's say we're going to apply a force, and I'm just going to give it as 10 newtons. And when I apply that force of 10 newtons, this is going to slide, and it's going to start out, and it's going to slide a certain distance, right? And we have some kinematic equations. We have our toolkit. And our toolkit says velocity final is equal to velocity initial plus acceleration times time. I'm not measuring time here. I'm not getting diddly squat, right? Not happening, ain't happening. All right, so that's kind of a scratch our head. So that equation's not going to work. Okay, but I do have velocity final squared is equal to velocity initial squared plus 2 times the acceleration times my change in distance. Well, I can look at this and I can come back and we can play with that in a couple of different ways, but I can actually calculate the acceleration. If I start out and I have a velocity initial, or my velocity final is going to equal 0. And if I have a velocity initial, I can find if it's 10 meters per second, and I know my acceleration, we're looking for acceleration, and I know my distance is equal to 10 or 1 meter, we'll just say 1 meter. If my final velocity is 0, because that's what's going to be down here at the end, my final velocity is equal to 0. Well, guess what happens? I get 10 squared plus 2 times my acceleration times my distance is got to equal 0. And this is going to be negative because it's a deceleration. It's a deceleration, but we can actually calculate the acceleration. So that's one thing that we can do. But if I know the force that I applied and I know the distance it went, one of the things that we'll see in this chapter is I can look at something called force is equal to a coefficient of friction times the normal force. And this is a normal force. And we can actually calculate a friction with my table. So if I did it on a smooth table, if I do it over the floor, we're going to see that distance is going to change because I've got a different coefficient of friction. So let's go back and take a step back and let's start drawing what we call a force diagram. So if I have an object on a table, we know that we have a force due to gravity. We have force due to gravity. But in order for it to not fall through the table's got to apply a force. And this is what we're going to call a normal force. And if I'm in equilibrium, the box isn't moving, that's got to equal 0. So my force due to gravity has got to equal my normal force because I'm not going anywhere, because Newton's first law says an object in motion remains in motion, or an object at rest remains at rest unless acted upon by an unbalanced force. So this, if it's staying at rest, these forces have to be balanced. That's what it's saying. And this gives us our idea of Newton's third law: forces come in pairs. I have to have this force due to gravity, and I have to have this normal force. The force due to gravity is considered the weight, and that's going to be mass times my acceleration due to gravity. My normal force has to balance that out, so my normal force is going to equal my force due to gravity. So let's take a block and let's put it on a plane here. And we're going to say that this is 30 degrees. And we've got a block on a plane. And this block, and I'll show you. So I've got my little paper here, okay? I've got a smooth mouse, all right? And my block is going to stay on my paper until it overcomes the force due to friction, and then it's going to slide down. So your pivot lab that you have on your pivots, it's actually looking at these forces on a ramp. But as long as my mouse is staying put, I've got a force that's keeping it there. Okay, I've got a force that's keeping it there. Now I've got a force that's sliding down. So let's look at my graph here. And so we know that my force due to gravity is always going to be going towards the center of the earth. It's always going to be going towards the center. So this is my force due to gravity. But I have a force that's being applied to the table, and I have a force that's going down from the table. And we said that there's got to be a force that's holding it up, and that's my force due to friction. That's my force due to friction. It's holding my block up. But let's look at this. This is in two components here. And this is why we start getting into vectors, and we talk about vectors, and we're looking at our vectors here, because this is the force perpendicular to the plane. And this is the force parallel to the plane. And if we remember our geometry from way back when, okay, it's been a while, but remember it, this angle here is going to be 30 degrees because it's related to my angle on my inclined plane. Now I have my normal force here. So there's my normal force that's coming out. So I can look at my forces parallel or my forces perpendicular. Well, my force perpendicular is going to be my force due to gravity cosine of my angle, and my force parallel is going to be my force due to gravity sine of the angle. And my force due to friction is going to be my coefficient of friction times my normal force. And that's one way we can actually measure coefficients of friction. Coefficients of friction are empirical. And we know that a rough surface is going to have a higher coefficient of friction than a smooth surface. These will come in a variety of tables. We can have a coefficient of static friction, and that's what's going to hold that mouse onto my block. That's what's going to actually hold my mouse onto the block. And then we have a coefficient of friction that's called kinetic friction. And my kinetic friction is the friction that is going to be in there as I'm moving. And my coefficients of static friction are greater than my coefficients of kinetic friction. So we start drawing our force items. So let's do, if we take an engine, take a train engine here. And my train engine has a mass of 10,000 kilograms. And we're going to fire it up and get it going. And we're going to apply a force of, we're going to do 500 newtons. We want to know the acceleration of the train. This is going to use our special case of Newton's second law. The sum of my forces is equal to mass times acceleration. So the force divided by mass is going to equal my acceleration. And I'm going to take my 500 newtons divided by 10,000. And that's kilograms. And if I do that, there's my calculator. 500 divided by 10,000 gives me 0.05 meters per second squared. So if you know your mass and you know your force, you can calculate the acceleration. And then you can even go back and utilize your kinematic equations. So that's one thing that we can play with. That we've got that's there. Now let's look, just so we've got grins and giggles here. Force or weight is going to be mass times gravity, which is going to be kilograms meters per second squared. And if I take force divided by mass, it's going to give me acceleration. That's kilograms meters per second squared divided by kilograms. And I end up in meters per second squared. So we can play with those units that we have. So Newton's first law is an object in motion. Newton's third law is forces come in pairs. And our Newton's second law, as we're going to use it, looks like this. And these are vector quantities. But let's stop and let's look at this. We're going to start and we're going to look at this a little differently, because I'm telling you that this is a special case. All right. So what Newton really said, and we're going to come back to this after we do energy. So it'll probably be after spring break, but we're going to come back to this. Newton actually said that I get impulse is going to equal a change in momentum. So if I'm bouncing a ball against the wall, I'm going to apply an impulse to the wall, and we know it's going to have a change in momentum because it's headed towards the wall and then it's going to bounce back from the wall. Impulse, Newton defined as a force applied over some incremental piece of time. So this comes very important because this is the difference between kicking a soccer ball or dribbling a soccer ball. How much force over the extended period of time that I get. Now, momentum is defined as mass times velocity. That's what our momentum is defined. We actually give it a lovely little letter P. But it's a change in momentum is going to be mass times velocity. Kind of an interesting thought process here, but we said that Newton's second law is F is equal to ma. Well, let's do a math trick. We're going to say force is equal to a change in momentum divided by a change in time. Well, my math trick says if I do this, I can have velocity times the change in mass over a change in time plus my mass times my change in velocity over a change in time. Well, we know what that is. We've been spending the last 7 weeks knowing exactly what that is, and that's acceleration. So what Newton actually said is, I have something that looks like this, where I have a changing mass over changing time plus mass times acceleration. Well, this term is a little odd. And for most of the time, like if I'm dealing with an object like a ball, it's not changing its mass. So this no change in mass, no change in time, this thing goes to 0 and I don't have to worry about it. And look what I have. I have Newton's second law, like we're playing with it in this particular chapter. That's an interesting result. However, if I'm dealing with rockets, space shuttles, something along those times, I can't disregard this term. And this is what actually allows me to do rocket science, is that I have to bring this term back. And that's why this is a special case. And we will come back to that when we start dealing with the momentum chapter. But I hate to tell you that that's Newton's second law, because that's not what Newton said. Newton said this, and we can get to this second law by doing that. So it's a special case. So it's a very special case. So let's do an Atwood problem. We'll start with an Atwood problem, and we'll look at some forces. So an Atwood machine is essentially a pulley. And off of my pulley, I have a mass. And I have another mass. And this is mass. We'll call that big M, and we'll call this little m. And if big M has got more mass than little m, and we let it go, we know what's going to happen. Because we've played with pulleys before. We know what's going to happen. This side is going to go down, and this side is going to go up. And it's tied together by a rope. We also know something special about this rope. And we're going to call this tension. We're going to call that tension in the rope. And if I think about this for a second, this is looking at my problem like this. If I have something that's hanging from a wire or a rope, we have the weight of the object, which is mass times gravity. And we've got tension in the rope. And if this isn't moving anywhere, guess what happens? My sum of my forces has to equal 0. And my tension is going up, my weight is going down, my tension is going to equal my weight. Well, we're doing the exact same thing over here, except we've got to deal with a couple of things. One is this: we know if these two things are attached, this tension has to equal that tension. Absolutely has to equal. So we know those tensions have to be the same. And if this is accelerating downward and that's accelerating upward, we know the magnitude of those have to be the same because they're tied together. The magnitude has to be the same, but they're going in opposite directions. So I'm going to draw a force diagram for this side. So my force diagram for this side is I have my tension in my rope. I have the weight of my object, and I have my acceleration. And I can write a force equation for this. Is sum of the forces is going to equal the tension minus my weight. But my forces are going to equal the little mass times acceleration. Now, these are still vectors. This is in the y direction because we're going to come back and we're going to look at our direction and our vectors in just a second, but this is in the y direction. Now let's look at this side. This side is I've got my big mass, I've got my tension, I have my weight, there's my tension, there's my big mass times gravity, and now I've got my acceleration going down. Well, now I'm going to write out my equation again. I have the sum of my forces, which is going to be my big mass times my acceleration, but I got to make sure I got my negative in there because this one's going down, that one's going up. But I still have tension going up, and I still have my mass times my gravity. I don't know tension, and I don't know acceleration. Don't know tension, and I don't know acceleration. But this is equation 1, and this is independent of this equation 2. These are both independent. I have 2 equations, 2 unknowns. So equation 1 is going to be little m times acceleration is equal to t minus mg. And I have minus big M times acceleration is equal to t minus big M times gravity. I can do a mathematical trick. I'm going to do my mathematical trick. I'm going to multiply this by minus 1. And that says I have little m plus big M times acceleration is equal to t minus t is 0. And now I have plus big M minus little m times gravity. So I just did that as my 2 equations, 2 unknowns. I can solve for acceleration. Acceleration is now big M minus little m divided by little m plus big M times gravity, and that gives me my acceleration. Then I can plug that back in there to get my tension. So I'm playing with what my sum of my forces are going to be. And that gives us that Atwood's type problem. And that's what these are called. These are called Atwood's problems. That you can play with those particular masses. So we have that Atwood's problem. We can do, let's see. We can do equilibrium problems. So I've got an object that's hanging down, and it's being strung with this wire, and this is 45 degrees. And this one over here is being hung in this one, and this is, we're going to make that 60 degrees. And we know that this has a mass to it, so that's mass down. We want to know the tension in those two sides of my object. If it's an equilibrium problem, it says that the sum of my forces are equal to 0. The sum of my forces are equal to 0. Hang on. Somebody joining us? All right. But this is tension 1 and that's tension 2. So let's look at this because now we've got 2 dimensions here. Well, we know we can divide our vectors because we can divide our vectors. So this becomes T2 cosine of 45 degrees is the tension of 2 in the x direction. T2 sine of 45 degrees is the tension of T2 in the y direction. I can do the same thing over here. This is T1 cosine 60 degrees, but we're going to have to go negative because this is going in that direction. And this side is T1 sine of 60 degrees in my y direction. So now I'm going to have the sum of my forces in the x direction is going to equal 0. And I'm going to have T2x minus T1x, or I'm going to have T2 cosine 45 degrees minus T1 cosine 60 degrees is equal to 0. Well, now I'm going to look at the sum of the forces in the y direction. It's got to equal 0, but now I have T1y plus T2y minus the weight of my object is in my y direction. So now I get T1 sine of 45 degrees plus T2 sine of 60 degrees minus mg is equal to 0. This is one equation. This is 2 equations. 2 equations, 2 unknowns, T1 and T2. Those are my 2 unknowns. But this one I'm going to solve a little differently. I'm going to go ahead and say T2 cosine 45 degrees is equal to T1 cosine 60 degrees. T2 is equal to T1 cosine 60 degrees divided by the cosine of 45 degrees. So now I've got T2, so I can plug that in there. I get 0 is equal to T1 sine 45 degrees plus T1 cosine 60 degrees sine 60 degrees divided by cosine 45 degrees minus mg is equal to 0. And then it just becomes a problem where you plug in the numbers and you solve for T1. And that was one of those applied example problems. We have to cover a couple more things. One is looking at Hooke. And Hooke says if I have a spring, and he actually goes in, if I apply a force to my spring we know what happens. If I apply a force to this spring, this is going to change its length. And if I look at my force times my change in length, and if I have a nice spring that's not deformed, I get a straight line. And this becomes Hooke's law. And what he says is that the magnitude of the force is going to be equal to some constant times my change in length. And we can utilize that, and my spring constant here, we can calculate that. That's the slope of this line. And I can have Hooke's law that we do. Now, typically what you'll see is Hooke's law is going to be listed like this. Because this is a restoring force, if I'm playing with a spring, it's trying to get back into its shape, but it's a restoring force. So we have another way of looking at something more in line with the system that we're playing with Hooke's law. So we can actually figure this out. So this is kind of fun. So I can take a spring here, and we can start out with the spring has a length L, and we're going to say that that spring has a length of 10 centimeters. And then we're going to hang a hook on it with a mass, and we're going to give this a mass of 0.050 kilograms. And when we do this, it's got a new length, and my new length is going to be 15 centimeters. We can actually calculate this constant because of the magnitude of my force, which is going to be mass times gravity, is going to equal my spring constant, which is what I'm trying to figure out. And we're talking the magnitude here. My spring constant times my change in length. So mg divided by my change in length is going to equal my spring constant. And that's going to be in Newton meters. And if I do this, I have 0.050 kilograms divided by 0.15 minus 0.1. And I'll plug that into the calculator. 0.05 divided by, looks like 0.05. That's going to be 1 Newton meter, and I can actually calculate a spring constant. So that's Hooke's law. And at the very beginning tonight, I said, hey, this is one of those situations where we've got the stuff that's going on, and Newton was trying to explain the Earth-Moon system. And we want to look at Kepler's 3 laws. And Kepler's law says, the first one is, here's my good old sun. And his first law says, planets have an orbit like an ellipse. And the sun is at one of the focuses of the ellipse. Well, that's pretty cool. And it turns out up until about Mars, our ellipse has the 2 foci inside the diameter of the sun. So, and actually Venus has a nearly circular orbit. Mars is pretty close, but Venus is actually better. But it's nearly circular. So that's the first law. The second law says, as we sweep through a time period here, so the time that it takes for this and the time that it takes for that are the same, that the areas of these triangles are the same. And it's actually these calculations that Newton really started looking at. And then he says, all right, if we assume that my orbit isn't, I've really exaggerated it here in terms of an ellipse, I've really exaggerated it. But if you think of the moon and you think of Mars and you think of Mercury, what you'll see is that we can make an approximation that this is actually a radius and that my period and my radius are proportional to the thing is period squared and the radius cubed. Or vice versa. I didn't look it up tonight to remember, but that's Kepler's third law. But what's coming here, so I'm going to right here check this because this is one of those that I may be writing it backwards. But that's Kepler's third law. But what this did is when Newton starts to go back, he comes up with this law that the force is going to be proportional to the mass of one object times the mass of a second object divided by r squared. And it turns out that that becomes F is equal to G mass of one object, mass of two object divided by r squared. And that's going to work for universal planetary bodies. But let's take a second here. Let's think through this. This is a constant. We can measure it, and that's what the Cavendish experiment does, is it actually measures it. But if I'm sitting here on Earth and I've got my little object here, okay, those two things are so small that what happens is I get my universal gravitation, the mass of the Earth, divided by the radius of the Earth squared, times the mass of my object. And this for Earth becomes my acceleration due to gravity. And that's what gives us our weight, the mass of the object times my acceleration due to gravity. And this, if I'm sitting on top of the Earth, that becomes a constant, and I get Newton's second law again. So we can actually come out of this one is Newton's law of universal gravitation. But then I get Newton's second law here. So we get that piece as well. All right, folks. I'm guessing brains are loaded. So what I'm going to do is I did have a couple of folks that wanted to see a couple of solutions to the projectile motion problems. What I will do is I will do short videos and post those for you all so that you've got that. I wanted to make sure we went through an Atwood's problem. I wanted to make sure we went through got all of our tools here for forces. So we've done that. So I'm going to go ahead and let you guys focus on getting some work done. I want to double check something real quick before I let you turn you loose. You do have a quiz this week, but it should be pretty straightforward. And the homework for our forces doesn't come out until the end of next week. So we still have time to work on forces. But I believe actually what I'm going to do right now is I'm going to extend this quiz. That way we have more time, because I had set that up that we would have done this last week and we would have played with some more of that. So I'm going to actually move that quiz. You do have a quiz on WebAssign, but it's more on the projectile motion side of things than it is on forces. So I'm going to leave that one, but I am moving this Blackboard quiz. So let me get that moved. Hang on. Boy, it's moving slow tonight. Okay, I'm gonna have that one due there. All right. So it's been extended till after our next meeting. And I haven't posted the weekly survey, but I will by the end of the night. I will get you a weekly survey right now. I will get it right now so it's in there because yep, that's how I keep track of where people are getting challenges and things like that. So I will do that. I'm just going to stop recording while I get that fixed.